Okay, so in this video, we will revisit matrix multiplication and linear systems, and we'll finally understand why we define multiplication between matrices the way we did. And the reason is because it meshes perfectly with linear systems. Consider a very simple linear system. Say we look at 5x plus 3y equals negative 2. Second equation, 6x plus 8y equals positive 1. If you were to solve this linear system, of course, as always, we would look at the augmented matrix. So we would have the first column for the coefficients of x, the second column for the coefficients of y, vertical bar replacing the equal signs, the constant terms would be negative 2 and 1, and the coefficients are 5, 3, 6, 8. And you would simply row reduce the augmented matrix, and then you would find the solution or solutions to this linear system. Let's try and find a different way to look at a linear system. Let's look at the left-hand side. And if you notice, this looks like a row times a column matrix, right? If you remember how we multiply a row times a column, we multiply corresponding entries and we add them up. So 5 times x plus 3 times y, this looks like, I'll put it here, a row that is given by 5, 3 times the column xy. 5x plus 3y, this would be a 1 by 1 matrix, and this is equal to negative 2. Look at the second row. Again, 6 times x plus 8 times y equals 1. This looks like a row that is 6, 8 times the column xy. Once again, the result is a 1 by 1 matrix, which we can think of as a real number. And we would get 6 times x plus 8 times y equals 1. So you see that every equation of the linear system is a matrix multiplication between a row and a column. Well, we can easily combine this into a single matrix multiplication equality. Think of it. We can form the matrix that we'll call A of coefficients in the same way as we did for the augmented matrix. The first row is 5, 3, the second row is 6, 8. We now have a 2 by 2 matrix, which we call A, times, well, if we want the first constant term, we'll have to multiply by xy, second constant term also by xy. And so we multiply by the vector of variables, x and y. This will label as an uppercase X, the column vector, the column matrix that contains the variables, equals. Well, let's see. Let's multiply this out and double check that we're okay. This is a, I'll just rewrite it here, 5, 3, 6, 8 times xy. A is a 2 by 2 matrix. Uppercase X is a 2 by 1 matrix, so multiplication is defined. And the result will be also a 2 by 1 column matrix. And if you think of the first entry, well, take the first row, 5x plus 3y. Second row, 6x plus 8y. And this is the result of A times x. And now if you think of it, if you want the equality to be equivalent to the linear system, well, what you have on the right must be a 2 by 1 column matrix. And to have an equivalence between the linear system and our equation here, well, 5x plus 3y must equal negative 2. And 6x plus 8y must equal positive 1. And we call this vector B for the column vector matrix of constants. And you see now we have a different way of looking at a linear system. You have the equations explicitly, then you can jump to the augmented matrix, or you can rewrite this as a matrix equation. Matrix A is the matrix of coefficients. Matrix X is the column matrix of variables. And matrix B is the column matrix of the constant terms. And that's it. You can always rewrite a linear system either in its augmented matrix form or as an equality in the form of A times X equals B. And this is always true. Let's consider one more example. What if we had two equations and three unknowns? Well, everything would work the same way. Suppose we do 2x minus 3y plus 6z equals 8, and x plus y minus 5z equals negative 7. Well, again, we can rewrite this in two different ways. You could rewrite the linear system as an augmented matrix. So we have three variables, x, y, z. The constant terms, 8 and negative 7. And the coefficients, 3, negative 3, 6, and 1, 1, negative 5. You could also rewrite, as we have just done, the linear system in the form of a matrix equality. This will be equivalent to the matrix A, the matrix of coefficients, 2, negative 3, 6, 1, 1, negative 5, times the vector of variables, x, y, z, equals the vector of constants, 8, negative 7. So the linear system is equivalent to the augmented matrix, and it's also equivalent to this matrix equality. Once again, we call the first matrix A, the matrix of coefficients. The column vector of variables we call uppercase X, and the column vector of constants we call uppercase B. And you can easily check again that this equality is equivalent to the linear system. Multiply the first row with the column, you get 2x minus 3y plus 6z must equal the corresponding entry, which is 8, check. Second entry, x plus y minus 5z, check, must equal the corresponding entry, that is the second entry, negative 7, check. And so our conclusion is any linear system can be put in an augmented matrix form, and also in the form of a matrix equality, AX equals B. And now let's consider an example and see what happens when the matrix A is an invertible square matrix. We can solve the linear system in a different way. We will consider a 2 by 2 matrix just for the simplicity of the calculations, but the idea works the same for any square matrix A that happens to be invertible. And here's the idea. If I gave you a system where A was a square matrix, you could always, of course, look at the augmented matrix and we'll reduce and find the solution or solutions that way. If A happens to be invertible, then you can find the solution in a different way. Think of it. You have the equality AX equals B, and A inverse exists. So why not? Because if you think of it, we're trying to solve for X. We're trying to solve for the variables. Well, solving for X would mean canceling A. Well, you can cancel A using A inverse. So as AX equals B, we can multiply both sides on the left by A inverse, and we'll get A inverse times AX equals A inverse times B. But A inverse times A is just I, and so we are left with I times X equals A inverse times B, but I times X is simply X. And so you see, if you have a linear system, you can rewrite it in the form AX equals B, And if A happens to be an invertible square matrix, you can find the unique solution vector x simply by doing A inverse times the vector of constants. Let's consider a simple example, as I've just said, of a 2 by 2 matrix. But the idea works for any invertible square matrix of coefficients. So here's the system. We'll take 5x plus 3y equals negative 2. 6x plus 8y equals 1. Let's solve this linear system using the augmented matrix and row reduction. Well, let's not multiply by 1 over 5. Let's do row 1 minus row 2, and then we'll negate row 1 to try and avoid fractions as long as we can. So 5 minus 6, negative 1. 3 minus 8, negative 5. Negative 2, negative 1, negative 3. Second row stays the same. We negate now row 1 to get our first leading 1. Well, we have our leading 1. Let's kill the 6 that is below. So row 2 minus 6, row 1. 6 minus 6 is 0. 8 minus 6 times 5, 8 minus 30, negative 22. 1 minus 6 times 3, 1 minus 18, negative 17. To get our second leading 1, here we have no choice but to introduce fractions. We'll do negative 1 over 22 times row 2. We now have the row echelon form of the matrix, and if you notice, both x and y have a leading 1, and so they are both leading variables. Hence we have a unique solution. So here we don't get the reduced row echelon form. We will simply solve the system using backwards substitution. So we first solve for y. Y is 17 over 22. And we can now solve for x. X is 3 minus 5y, so minus 5 times y, but y is 17 over 22. Let's simplify. We have 3 minus 5 times 17, 85, over 22. Common denominator, 66, minus 85, over 22. 66 minus 85, negative 19, over 22. And now we have our unique solution. The system has a unique solution being x equals negative 19 over 22, y equals 17 over 22. Okay, so we have just solved this 2 by 2 linear system using the old method of row reduction. Let's now rewrite the system in the form ax equals b, and then solve the system using the inverse of A. So we get 5, 3, 6, 8, that's matrix A, times the vector of variables x, y, which we call uppercase x as always, equals the vector of constants, negative 2, 1, which we call b. This is equivalent to our linear system, and we know that quite simply, x is A inverse times b. Well, let us find A inverse. As A is a 2 by 2 matrix, we have the shortcut formula. A inverse we know will be 1 over AD minus BC. So 5 times 8, 40, minus 3 times 6, 18. We flip the diagonal entries, and we negate the other two entries. Well, 40 minus 18, 1 over 22. So far it's looking good. Times 8, negative 3, negative 6, 5. And now the only thing left to do is multiply b from the left by A inverse. And so, the vector of variables x given by lowercase x and y equals A inverse b, 1 over 22, 8, negative 3, negative 6, 5, A inverse times b, the vector of constants. 1 over 22, we'll leave it outside for now. So what do we have? 8 times negative 2, negative 16, negative 3, negative 19. Second entry, positive 12 plus 5, positive 17. If, of course, you multiply each entry by 1 over 22, you get negative 19 over 22, positive 17 over 22. And so if you look, what is our conclusion? Well, we have an equality of column matrices. They can only be equal if they have the same corresponding entries. So if x equals negative 19 over 22, and if y equals 17 over 22. And if you just look up, this is exactly the solution we obtained using row reduction. X is negative 19 over 22, y is 17 over 22 as our unique solution, which was found in the exact same way using A inverse instead of row reduction. And that's it. If you had a larger square matrix, the only difference, x would still be A inverse times b as long as the matrix A is an invertible square matrix. The only difference is you wouldn't find A inverse using the shortcut formula, but you would find A inverse using row reduction. That's it.